all once again to my lecture on quantum mechanics. Okay? Very good. I am happy that all of you are coming in large numbers, and I find that you are very, very sincere. And this is the first prerequisite for learning as well as teaching of any subject. Unless there is a line in Ramayana which says, Srota Bhakta Jnana Nidhi Katha Ram Ki Bood. So, the story going on in front of you on this fundamentals, basics of quantum mechanics is really abstract, is really good. And for this, I personally make it a point to make my lectures as interesting as possible, to make them as much comprehensible as possible. And I find that you people are equally responsive to my lectures, to my teachings, and that really pleases me. I am extremely happy that you are also making sincere efforts, unless you try to hear me properly, attentively, carefully, sincerely, with your heart, soul and mind. It becomes difficult. Okay? You look at various books on quantum mechanics, even the ones that I am mentioning, you find that it's not so always easy to pick up the basics coherently, correctly, okay, and to make sense out of it. So this is almost free of cost that I am there in front of you every day, right? And yes, I mean the private universities, they charge you almost 7 to 8 times than this money, okay, than you pay at Delhi University. So it's almost free of cost. This system exists in India, fortunately, so that everybody gets a chance. Okay? Almost on the same pattern, German system works almost on the same pattern, but not the American system. There the higher education is extremely expensive, out of reach for the people even living there. Even for the Americans, it's difficult to pay the fees and to support the child for this kind of education. So I am happy that you are making good use of it. Okay, very good. So now we can gradually get back to the basics. So first couple of minutes to recap what we have done, and then we proceed further. This always pays. We consolidate things that we know, then we move ahead, we move forward to become new. Okay. So, so far, I mean, especially in the previous lecture, one or two, I have mentioned to you about this famous experiment, Stern-Gerlach experiment, and they were able to figure out that the two traces that are seen in these spectral lines really cannot be explained with the theory of orbital angular momentum alone. So you need something extra, because the theory of orbital angular momentum would predict that when you pass the silver atoms through the inhomogeneous magnetic field in the spectral lines, I would expect only one line corresponding to little l equal to 0. Okay? Because each component of L has 2L plus 1 eigenvalue. So L equal to 0. There will be only one eigenvalue. There will be only one pair. But you obtain 2 in a state. So these guys, Uhlenbeck and Goldschmidt, they propose a very basic fundamental idea which maybe 1 in 1,000 people only can get. And once in a blue moon, you get this kind of enlightenment that, oh, this could be due to something missing in the, that is actually the birth, origin of the so-called spin angular momentum. So, they think, oh, there is something wrong if we take only about the orbital angular momentum. There must be something else in addition to L. And that was proposed to the spin angular momentum denoted by S, okay, with its magnitude S cross by 2. And it was proposed that, okay, let it have spin 1/2 plus or spin 1/2 minus, spin up, spin down. Okay. So these two eigenvalues then were assigned to S. They were plus minus S cross by 2. Okay, where H is your Planck's constant. And if that happens, then you can easily explain the magnetic moment associated with the motion of the electron. Okay. So electron is having not only the orbital motion, it also has the spin motion. And you see, this is the beginning of the advent of the entire modern physics. Okay? So, then there were lots of subsequent developments in theory as well as experiment, and many great guys, they worked around the globe. So, the last 100 years or so, they really saw the advent of so-called modern physics or the quantum physics, which was not known until that time. Okay. However, we might have been advanced, or other civilizations in the world may have been advanced, but these are only stories. We really did not know the nature in the form that we know it now. Okay. This is, I respect all the old literature, but you see, this modern science, as we understand it today, really did not understand in the past. Okay. There were beautiful ideas in the past. I know myself personally that there were many great ideas. Today I would run out of time if I would talk about them, so maybe we will take them up some other time. I would tell you myself, lots of beautiful, very rich ideas that existed in our literature, in particular in the ancient Indian literature, but this is nowhere near the realization of this modern science. Okay? So we really have to appreciate this present day current understanding of the modern physics. Okay? Fine. Now these three matrices called Pauli-spin matrices, they were given by Mr. Wolfgang Pauli, who was working in Dirac in Switzerland. Beautiful lake there. I just been there a couple of times, really enlightening. But I find my place here also equally enlightening. You see, you need the peace and cool of your mind, concentration of your mind. Then you really don't realize whether it's 40 degrees Celsius outside or not. You have to be peaceful from inside. Okay? Then you can literally great things, discover great things sitting at any point of the planet. Okay? You don't have to necessarily sit in one or the other particular place. All are equally important. It's all one Mother Earth. Okay? So far, as we know, there is no intelligent civilization elsewhere, at least within our own solar system. There may be exoplanets, there may be life, they may be more intelligent than us, but nevertheless, we really have no contact with them. Okay? So, even if they are there, they are really of no direct use to us. So, this is our intelligent civilization, and it has taken us 13.7 billion years to develop up to this stage. Okay? So, it's a continuous development. Okay, when the universe was born, at the time of the Big Bang, 13.7 billion years have passed since then. Okay? And so, our age is really not 20 or 60, but it's really 13.7 billion years old we are. Okay? And or 13.7 billion years young we are. Okay? So then I picked up one particular matrix, namely sigma z. It is a very simple looking matrix, 2 by 2 matrix, and we calculated the eigenvalues and eigennormalized eigenvectors of this matrix. Let me just mention it to you once again. So, sigma z equal to sigma 3 equal to 1, 0, 0 minus 1, and s hat is s cross by 2 sigma z, and then the eigenvalues of sigma z are plus minus 1, eigenvalues of S hat would be plus minus S cross by 2, correct? And the normalized eigenvectors are 1, 0, and 0, 1. Okay? For both of them, because even for S hat, when you determine the eigenvector, S cross by 2 would cancel out from both the sides. Okay? And therefore, the normalized eigenvectors that you would obtain would be 1, 0 and 0, 1. Okay? So now, look at the cases of Mr. Pauli. He was able to use this on an industrial basis. You see? Just on a commercial basis. Very beautiful. Okay? In a very intelligent manner. And he developed the concept of so-called two-component formalism. Pauli's two-component formalism. So, he gave new names. This is one zero minus is defined as 0, 1, and then you can take the complex Hermitian adjoint of this. This would be then 1, 0, and Hermitian adjoint of this would be 0, 1. I like to call it E1, and this as E2. Then this would be my E1 dagger. This would be my E2 dagger. Okay? Later on, we can even stop putting these caps or S on each E1, E2, E3. It may not be needed. Once we understand its meaning, we can express it in words. Okay? So, because otherwise notations become too clumsy. Okay? For that reason. So now once you know this, you can immediately calculate this kind of an object. This would be E1 dagger, E1, and this would be 1. Now dagger goes 1, 0, and 1, 0, and this would be 1. Similarly, minus, this would be E2 dagger, E2, and this would be 0, 1, and 0, 1. This would again 1, and if I calculate this would be E1 dagger, E2. This would be 0. You can do it. Similarly, minus plus. This would be E2 dagger, E1. This would again be 0. Okay. So, what does it tell us? It tells us, oh, I have discovered a very beautiful property of these things, that they satisfy the completeness property. Sorry, this is orthogonality, E1, E2 equal to 0, or E2, E1 equal to 0, so they are orthogonal. And this tells me E1 square equal to 1, E2 square equal to 1, so that this property is called as completeness property, and its meaning is that their magnitudes are unit. They have unit length. Okay? So, if these two properties are satisfied together by some objects, then this property is called as orthonormality. And we could easily use them as the basis vectors for our calculation. Here we are talking about only a two-dimensional complex vector space. We could talk in general about the n-dimensional vector space. And so, here in three dimensions, for example, they would not be called, one is two-component formalism applies to two-dimensional space. But here, I could have E1 equal to 1, 0, 0, etc. and so on. E2 equal to 0, 1, 0, 0, 0, etc. and so on. I could construct the basis vectors for the n-dimensional space. And now we would need some additional properties which we would like them to satisfy, or we would like to verify if they satisfy those properties or not. So, okay, now I first define a few more things, and then you see you will discover that also maybe throughout this course I am only teaching you the alphabet of the quantum mechanics, not really starting to do quantum mechanics. It takes the lifetime to be able to do. Okay, so let me first define some let's say A. Let it have components A1, A2, A3. Let me just see A1, A2, and this A has components B1, B2. Then let us see what is the definition of a scalar or inner product. So inner product, let us say BA or AB, let me call it AB. So if I have this as A, then this A would be A1, A2, and this B would be A1, B2. Is that okay? So I have this a bra of A, which would be A1, A2, and this is cat of B, which is B1, B2. And now you can define this times this, so A1, B1 plus B2, B2. And obviously this is a number. So it should obviously, even conceptually, in a product which was called a scalar product in your vector calculus in the three dimensions infinite space that you get in your first year, always was a number. A because theta, that was a number. Fine. So if I had higher dimensions dimensional space, then I would have A1, A2, and so on, and I would have B1, B2, and so on, and then this guy would be A1, B1 plus A2, B2 plus AI, BI. So you see, generalizations are very straightforward, and I personally like to memorize things in a smaller dimension. Once I understand it in two-dimensional space, I can easily extend it to three or higher dimensional spaces. Alright? It's easier to understand the physical meaning of these things and even the mathematical formulas or the formalism. Okay? So that's my way of doing the things. Let me then also give you some more definitions. Some of them you will be doing. Could I remove some of these things from here?
Yes.
Yes, let me remove all the way up to here. You see, this we have already been making use of here. Okay? It's difficult which thing you talk first, which thing you want to talk later. So they are very closely near each other. Okay? So we don't always go into the problem of the egg and the chicken, but we try to understand some of the basic things. So there is this normal product of two matrices that we call A and B, and these are two matrices to be defined as A11, A12, A21, A22, and B11, B12, B21, B22. Then you can easily multiply this. All of you know it, but for the sake of completeness, let me give it to you. So this is 6 times 6. This is A11, B11 plus A12, B21, and so on. Can you complete this, or do I do it? You can complete it?
Yes.
Okay, very good. So that's how you do it. And then let me define some further things which you are not yet familiar with. Okay? So let me give you yet another definition, and let me write it on this side, which I would be using very often. So A, B. This is called as the outer product of A and B, and it is correctly to be written as this. So outer product of the two matrices, and let me stick to 2 dimensions. So my German way of notations, then I am working in 2 dimensions, and this is A1, A2, and this is bra of B, and B2. This definition you may not be familiar with so far. Okay? So this could be new, alright, you multiply it, A1, B1. Okay? So this is, we are defining it to be equal to this A1, B1, A1, B2, then A2, B1, and A2. Okay? Alright? Alright? So this product is called as the outer product of 2 state vectors, and it is to be noted usually everywhere in the books. Even I might keep writing it like this, but it is understood that this is defined as this. This is the correct definition, and this is defined as this. So you see from here that this guy is a column vector. Okay, it's a matrix, a column vector. This guy, this one, is a column, so it's a row matrix. Okay, another plane matrix, but in the horizontal. Not a column, it is not. One is a column, one is a column. And here you find that this is a fact matrix. Fact. Okay? So, then you are talking in terms of 3 here, you get still fact matrix 3 by 3. When you take 4, n by n, you will large fact matrix. And later on, at some point of time, maybe already tomorrow, I would tell you in details, I would introduce the operators, and then I would say that the operators could be represented through matrices. So you already find that, oh, this guy is some kind of, this guy was a number. Scalar products, they were number. Whether 0 or 1, but they were number. Or whatever, they were number. But this kind of a product, which is called the outer product, is an operator. This is an operator. Outer product of two vectors defined in this lesson is an operator, and is represented by a set matrix according to this rule. Is that okay? Very good. So then let us try to see. I can remove some of the things from here. Could I? Okay. So if you like, I can even remove it to this place.
Yes, sir.
Okay, well, up to this place. Okay? Up to this place. Alright? So, this let me preserve for the time being. Okay? And of course, if I need, I could do this. Okay? Now, I postulate or define the new property, and let us see if it works or not. So, let me consider summation over I equal to 1 to 2 Ei and Ei. So when I say I goes from 1 to 2, then I am considering a two-dimensional space, and this I claim that this would come out to be equal to 1. Let us now, here is the calculation. All of you please try to verify it along with me. I do it here, you do it on your notes. Okay? On your notebook. Let us see what do we arrive at. So this is E1 plus E2, then I will introduce E1 outer product of E1 plus E2 outer product of E2. Now this is 1, so where is this? If there, so 1, 0, outer product with, no, this is wrong. This has to be 1, 0. Okay? This is a cat vector and this is a dot vector. So 1, 0 plus E2 is again a cat vector. No, E2 is 0, 1 and 0, 1. Is that okay? Very good. Now make use of this definition which is given here. Let me enclose it in a box, and so this according to use that rule, so 1, 1, then 1, 0, then 0, 1, then 0, 0. Plus do the same thing, 0, so 0 into 0, 0 into 1, 0, 1 into 0, 0, 1 into 1 is 1. Okay? Alright? Very good. Now you can add them up. So this is 1, 0, 0, 1. So this is the unit matrix 2 by 2 unit matrix. This is a 2 by 2 unit matrix. What is the unit matrix? It's a matrix where the diagonal elements are 1 and the rest of the elements are 0. Okay? Very good. So, and now if you extend this definition to 3 dimensions, you should again get it 1. To extend it to 4 dimensions, you should again get it 1 means unit matrix. But then in the 3 dimensions space 1, 0, 0. So in 3 dimensions, in 3D, this is 2D. Okay? In 3D, this may be 1, 0, 0, 0, 0, 0. This may be 0, 0, 0, 0, 1, 0, 0, 0. And this would be 0, 0, 0, 1. And then this would be 1, 0, 0. Here, before this, the line earlier than this would be, this is equal to sigma pi, I equal to 1 to 3. I equal to 1 to 3. Okay?